Hello, everyone. Can you hear me? Okay, so good morning, good afternoon, good evening, depending where you are. Um, Welcome to the first keynote sessions of iiWAS and MOM 2020. It's my great pleasure to introduce our first keynote, Professor Liming Luk Chen. He's a professor of data analytics, director of research from Ulster University in United Kingdom. I'll introduce a little bit of biography of Luke. Dr. Liming Luk Chen is a professor of data analytics, director of research for the School of Computing, as I mentioned, at Ulster University. And his current research interests include data analytics, pervasive computing, artificial intelligence, user-centered intelligence systems, and their application in smart healthcare. Dr. Chen is an IET fellow, a senior member of IEEE, a co-founders and co-directors of the IEEE CIS User-Centered Smart System Task Force. He was the coordinators of the EU Horizon 2020 project and has served as the principal investigator for the EU AAL PIA project, the Mobile Sage project, and the FP7 Michelangelo project, and a number of projects funded by industry and third countries. He has over 230 publications in internationally recognized journals, book series, and conferences. He's very active, chairing many conferences and international workshops. He's also associate editor of IEEE THMS, assistant editor-in-chief for IZPCC, and guest editors for IEEE THMS, PMC, and IJDSN. He has delivered over 20 talks, keynotes, and seminars in various forums, conferences, industry, and academic events. And Dr. Chen has served as an expert for research funding assessment for UKRI, EU Horizon 2020, Canada, Chile, Netherlands, and Denmark. This morning, his talk is about interweaving IoT, data, and intelligence towards future healthcare ecosystems. We're very eager to hear what he's presenting today. And on that note, I welcome Professor Luke Chen.
Thank you, Eric, for your kind, generous introduction. I just want, hello, everyone. Good morning or good afternoon in Asia countries. So I just want to check with Eric or everybody, can all of you hear me speaking? Can you hear me? Hello?
Yes, I can hear you.
Yes, yes.
Oh, okay, great. So, okay, it is really my honor and pleasure to have this opportunity to share my research and also my research visions with all of you. Yeah, it's a special time. It's just a pity, you know, we cannot meet face-to-face in person due to the pandemic. Nevertheless, I think this is also probably a best testimonial, you know, showing how health and care so important and how they impact our life, our society. So seeing that, talking about healthcare in this backdrop indeed make much sense. As you can see, so the talk I'm going to give is about interweaving IoT data and intelligence toward the future healthcare ecosystem. So what I'm, let's see, oh, it does not move. Strange. Oh. Let's see. Yeah. So I will first briefly cover. Okay. I will first in this talk. I will first briefly cover the research context on smart healthcare, and then spend some time to describe or introduce our research activities in this area over the past decade, and also, the project we have been undertaking. And then follow that, I will describe a future healthcare ecosystem. And follow that, we'll discuss about challenges and opportunities, and followed by the conclusions. So probably most of us are fully aware we face global aging problems. As you can see from the diagram figures, the aging population in all regions of the world is increasing in unprecedented rate. Europe probably has the highest aging population, but look at the trend of the curves. Asian countries is picking up, and among them 80 years or over, that category of population is the fastest growing age group. This demographic change has two direct consequences. The first is the prevalence of aging-related disease. Just give you some examples. You see the Alzheimer, the diabetes, heart disease, arthritis, and cancers, and the more, the mental health, come to the fore, like depressions, anxiety, loneliness. So it is so prevalence, it's increased growing demand on healthcare services, and of course, leading to the shortage of health and care resources. As you can see, illustrated by these diagrams, the long queue in the hospitals, in the appointment system, and also the rising conflict between patients and the medical professionals. So that is the worst is down the line. The healthcare investment will be outpaced by the demand. So the situation will become worse rather than better. We have to do something. The second consequences is the change of the way of our society are structured. So as you can see from the right-hand top diagram, the distribution of the different age group of the population has changed, from 1970s to 2010, or then, projecting to the future 2050s. There are more elderly people and less, in terms of the percentage, young peoples. The consequences is, as you see from the left-hand side figures, the support ratio, basically the number of working age people per old person is dropping. So there's less support for our elderly society. This means, if you look at the diagram from our BBC, it shows one family, 5 generations with only one great child. So you can imagine how that children's future life will look like. So this shows, in the future, we all need to look after either ourselves or our relatives. So that's inevitably leading to the decline of the quality of life. So it's not about just those people who have the medical conditions, who are elderly, but actually the whole society. So it is in this backdrop, using technologies to help address the aging problem has emerged as a promising approach. Basically, how can we use the ICT technologies sensor network, mobile computing, data analytics, a multi-modal interaction to provide product services to support a wide range of health and care scenarios, such as to facilitate or to speed up the transition from acute medical condition intervention to preventions, to facilitate automated diagnosis and to support independent living and self-management of chronic diseases. Not only just for elderly people with conditions, but actually for the young, the middle age, for the public, and not only say for people at home, but in the community, at work, and on the move when they travels. The world relevant, related community has all realized these rising issues, and there are a wide range initiative in all countries. So just to give you examples, in the UK, we have EPSRs, the main physical and engineering funding council has a healthcare technology program. And in Europe, we have a healthcare program in both, last FP7 research program and the current Horizon 2020, and in the future, Horizon Europe, there are all is the main focus of the societal challenge. And in Europe, we also have a dedicated ambient assisted living joint program, try to facilitate the knowledge transfer and research translation from scientific research to industry, commercializing usage. And smart home has become one major realization of the technology-driven approach. It's referred to an augmented residential environment, which are equipped with sensors, actuators, and devices so that the residents or inhabitant in the environment can be monitored, the medical condition, the daily life, so that timely or context-aware assistance and support can be provided. So as you see the diagram, the left hand shows basically the rational, in a house environment, various sensors are deployed, to monitor relevant activities. And the right hand side, as you see, actually this is a real world smart home in the Republic of Ireland. It's called Great Northern Highland. And our team has spent several weeks over there to deploy the sensors. That is the way, monitor the sleep conditions. Just to give you a rough ideas. There are a number of research areas presented by a smart home. Actually, if you look at that, technically, it involves multimodal sensing. That is about design, deployment, and optimization of sensors. Where do you install the sensors? And then come to the active monitoring, data modeling and management. How do you collect data, store data, reuse data, and then about active recognition, behavior analysis, and user modeling, visualization, decision support, and the catering or provisions of the assistance. So it covers the whole life cycle of our system. Our team has focused, probably our research covers the whole life cycle, different phases, but the main focus, our research over the past decade has focused on activity recognition behavior analysis. So in the following, I will probably give you a high-level introduction to our research. We will not go to drill down to one particular piece of study into technical details, but I will introduce a number of different threads of research and give you an idea the breadth and the width of our research. And also importantly, it's based on that research, the findings which leading to what we talk about the ecosystem of healthcare. Yeah. So as I mentioned, our research focuses on activity recognition and behavior analysis. So just to give you a little bit very quick background, there are two main approach to activity recognition. One is data-driven. So it's based on data mining and machine learning techniques. Even used within the data-driven activity recognitions, there are two main types. One is, we say, generative modeling and recognition, such as hidden Markov, DBN, and POM-DP. They use these models. Another is called discriminative modeling and recognition, like nearest network, SVM, CRF, and the decision tree. Yeah. So the generic methodology, basically, you create a probabilistic or statistical active models, and then you use the pre-existing data set to train the active models, basically to learn active model parameters. And then use the active models as a classifier or as a clustering models for activity recognition. So the advantage and the disadvantage for this data-driven activity recognition is that it is able to handle uncertainty and temporal information. But the disadvantage is it suffers from the cold start problem. It requires larger scale pre-existing data set. It's also sensitive to unseen data. So basically, if the data does not capture what is happening, then there's no way you can train or learn what's happening. And another is it's very difficult to reuse. You learn something from one data set, from one cohort of users. It will not be able to transfer to a different cohort. Yeah. So there's another approach we call knowledge-driven activity recognitions. So that approach is based on knowledge engineering and artificial intelligence techniques. So again, the generic methodology is we acquire domain knowledge and heuristic about activities. So for example, in our daily life, we all know how to prepare a cup of tea, how to do hygiene, have a shower, or washing your clothes, or make a meal. Yeah. So then we specify active models directly using a knowledge representation formalism. There are different ways. Yeah. And then we can develop a reasoning mechanism and reasoning engines. So in these cases, performing activity recognition, is more or less equivalent to conduct formal logical reasoning, deduction, abduction. So because there are different ways of practical implementation based on the underlying knowledge representation formalism, you see there are different. There is a first order logic, logic, or action event theories, and even discrete logic. So you could select different knowledge representation formalism, then it will closely related how the reasoning, the inference, the mechanism, it will be implemented. Therefore, you choose different knowledge representation, that you will lead into a different set of technologies. The advantage of the approach is there's no cold start problem, because we start with knowledge from the domains, from experts, from the textbook. And it's semantically clear. We say when you model that, and logically elegant, because whatever conclusion you derived from such a system, you can always trace back. Yeah, we talk about, for such system, we say is sound or tractable. Yeah. But the disadvantage is people will complain if the model are static, one fit all, and incomplete, because it's difficult for knowledge engineers to capture all various mutations, different situations, and manually encoded that into knowledge models. No, we acknowledge this. So in our research, actually, we try to marry the strengths and mitigate the drawbacks from two approach. So we propose a hybrid approach, yeah, to activity human behavior analysis. So this diagram shows the process which can be depicted. You see, probably starting from the left hand, we're starting from environment, and then we apply knowledge engineering techniques. We can produce an initial knowledge model. We call it, in this part, yeah, ontologies. No, we know that knowledge model is not complete. Yeah, we cannot capture all of them. Doesn't matter. We created we call it seed knowledge models. Then we can apply them to real world situation, for activity recognitions, yeah, based on the contextual informations. Again, it will produce, some recognized activities, but if the activity has not been modeled, because the knowledge model is not complete, therefore it may not recognize all the activities. Doesn't matter. We know it's produced two results. One is recognized activities, one is unrecognized activities. Then in the third phase, we will apply data-driven approach, apply data mining, machine learning, data analysis techniques, and to learn new activities, to learn the way people perform activities. And then in the fourth phase, we will, improve, consolidate the initial knowledge models. Yeah. So this is an iterative process, I would say. So the first half, it will be knowledge-driven activity recognitions, and the second part, the third and the fourth phase is data-driven. In this way, modeling is not a one-off activities, as you can see, but it's an iterative, multi-phase process. And modeling and recognition is not separated, but they are interweaved. Yeah, so that both improve incrementally, both the models and the recognitions. So I will briefly go through what we did, because there are many different aspects in this framework. So the first, we develop our knowledge-driven activity recognitions. So we conduct the knowledge engineering, establish the conceptual and computational models for object, for activities. And then based on that, because we use ontology engineering, basically a description logic-based knowledge modeling, knowledge representation formalism. Therefore, we apply semantic reasoning for activity recognitions. And then we combine the semantic reasoning activity recognitions with data segmentation. Therefore, it support continuous progressive activity recognitions. So you may see in some slides, at the bottom, I include some papers. Basically, that is just some representative research output. All the that single slides is published in probably one or more papers. So here just give you a very high level what we did, and if you want details you can refer to the papers. So as we said, once we have the knowledge-driven approach, it's produced recognized, unrecognized activity traces. Then we develop a data analysis method. So in that case, we mine the unrecognized activity traces, basically to learn new activities, to expand the models, to improve the completeness. And then for those which activity has been already recognized, therefore we develop the algorithms, try to classify those recognized activity into different subsets. Basically, we want to learn user activity profiles. How do you perform a particular activities? You and me, all different people, all do them differently. That is how do we create user profiles. And then we will develop algorithms to mind how the user perform activities in a particular patterns. So that is the way we did that. Yeah. So, and another, in that overview framework, another piece study we have focused is about sensor data segmentations. So the question is, given a real-time data stream from multiple sensors in multiple formats, how to infer the activities being performed? You are thinking about an environment which has multiple sensors, each send or perceive activities. So in this scenario, we have two separate piece studies. One, as you can see, we analyze, characterize, different scenarios. The activity can be done sequentially, can be done interleaved, and in parallels. So we develop a time window based approach. Yeah, it's a non-tuple time window models. Another, we carry out a semantic-based segmentation approach. As you see, both study has published. Yeah, just give you ideas. We are not, when you talk about activity recognition, there are different use scenarios. Single user, sequential activities. So we address that, but also we have studies focused on interleaved, complex activity recognitions. This is referred to interleaved, concurrent, and parallel activities. We here describe a piece study. We combine discrete logic with temporal logic for modeling, and apply, as you see here, multiple agent system. There is a single activity, simple activity recognitions, and the complex activity recognitions, and also the sensor agents, multi-sensor agents, that's different ways. We extended the existing conceptual active models and create the static models and reasoning rules. That is another specific niche area we drill down. And this is show you our another research. So in a smart environment, it's full of uncertainty, incomplete information, or imprecise information. There are situations, sensor is faulty, and due to communication, the sensor data is missing, and there is a low batteries of sensor, therefore there is no signals. Yeah. And if you look at the activities, there's also different levels. If you think about you pour water to a cup or milk to a cup, what's the angle the water began, to the cup? How is it full or half full? So that is we are looking at, the fine-grained level of activity recognitions. So here we just show part of, we develop an ontological framework to capture the factual, uncertainty, incomplete knowledge. And then in the middle, you see here, this is a ontological representation of such knowledge. And then based on that, we develop an algorithm, to detect missing actions and sensor failure, and detecting incomplete actions, and also, detecting missing and incomplete actions under uncertainties. So that's give you an idea. So this is a number, you look at the framework, but we, over the past probably 10 years, we are working, drill down to cover the whole different scenarios and drill down deep. Yeah. And in the following, I will probably introduce some example project we have been working in the past several years. So one is Michelangelo is patient-centric models for remote management, treatment, and rehabilitation of autistic children. It's basically to try to bring the assessment and the therapy of the autism children of the clinical environment and develop a patient-centric home-based intervention framework. So as you can see, this is the system. It supports both home and clinic monitoring. So this is a home environment. So we will apply videos to monitor the activities and also use the ECG to monitor the brain activities. When the children perform serious gaming or conduct, predefined learning materials, all those information, will be captured and the data analyzed, and then, assessment about his condition will perform, and then provide, different user interfaces for both clinicians, doctors, and parents, relatives, and professional carriers. Each of them see different information. Therefore, they are in a best position to support them. So another project we call MOSKUS, basically to develop a user-friendly, adapted medical self-management tools for patients suffer from arthritis. Yeah, you see here. So this is show you the starting point is a person, has been diagnosed with arthritis and has already undergone through the initial treatment in a hospital. Now he go back home, and in this environment is in the home, the MOSKUS infrastructure will be deployed. So you see there are various sensors. So normally the patient need to go back every 7 days, go back hospital to see the doctors to do the assessment, measurement, and now the patient can do that at home environment by self-management. So you see here there's mobile apps for the patient to self-report, the conditions, but there is also sensors will capture the behavioral and the medical vital sign data. And you see here on the right-hand bottom part, there is a decision support system to help carry out the assessment, provide recommendations. Yeah. Another project is funded by IADL joint program. It's called Personal Instrumental Active or Daily Living Assistant. So basically, it's aimed to provide helpful instructional video clips to support elderly people, to help them to conduct activity at home independently. And also it's try to say the videos can be made by relatives, children's rather than professionals. So here again you show in a home environment, various sensors are attached to an object like a washing machine, like how to do a pedicure, yeah, how to do washing. If you are 78 years old or over 80 years old, you get a new washing machine, very modern, automatic, but you don't know how to operate that. And your children can produce videos and upload into a cloud and a whole system. And they also provide a social network, so they can help with each other. So this is another project we did that. So the final project I will introduce actually is a crossing that is advanced technology and platform for smart assistive living. It's supported by Horizon 2020. It has 10 beneficiaries, which Chen 15 early stage researchers with a funding budget, nearly 4 million euros. And I think here I give you a rough project detail, but the key is the research program. It covers all main underpinning technologies for healthcare, from sensing, monitoring, to context inference and behavior analysis, then to the personalization, adaptive interaction, and open smart health platform. And also it address 4 different use scenarios, like assisted living with cognitive impairment and self-management of chronic disease, and patient empowerment, and then mental health. So this project, produced about over 70 research papers, all different aspects. So that's it's connected by myself, and so basically I give you a very broad, high-level introduction to our research over the past 10 years. So not only about what's happening, but most importantly is from the research, we find out there is so much which have already been done, and the concept and the methodologies are clear. Technologies and the proof of concept application are working, but there's a gap. Yes, no matter if you look at the project I present, they cover from fundamental research like crossing, they cover the development project like the MOSKUS and the Michelangelo, but they also cried AL is really trying to put things into the real world use scenario, but still we do not see any killer application widely used at the moment. Yeah, of course we know there are fragmented technologies and systems in silos, inoperable, operatables. So that's the things happening. And if you look at where we are at the moment, the technology push has become stronger and stronger. So just to give you an idea, you look at that, the IoT proliferation and the penetrations. We all know everywhere in the daily life, the wearables, the sensor network, the smart object is growing. It's following the Moore's law. Every 2 years, it's doubled. Yeah, and similarly, you see the data, the algorithm, the computation power. It's also growing. Yeah, and we also see the confluence from different aspects, from the internet, huge amount of objects, they produce huge amount of data, and it's on cloud, on edge, and AI technologies. Yeah, technology is developing so rapidly. It's opened so many opportunities, But the question is, it does not reflect, in our daily life in terms of health and care. So that is some motivating and yet pressing questions. How can we, interweave IoT, data, and intelligence to make what we have been working about smart healthcare, it work in real-world context? How can we integrate them, technology and services into the existing healthcare systems? What is the business model and the service models? How can we operate them, make them, smoothly and fill into the mainstream healthcare service provisions? I think it's this motivate us, to think about. So that's how the future integrated healthcare ecosystem come into a being. So I just probably explain the ideas, use the scenarios. So you think about it's a moment. If you are a patient or you are older people, you have some conditions or you need some help, you go to see doctors, you go to see carers, and you describe your medical conditions, your care need, your well-beings, and what the doctor or care provided. They give you a medicine, you take home, you take medicine at home. That is what is happening. And then you need to come back, you make an appointment, waiting for 4 months or 3 months. Yeah. But what's the future? Future we envision. When you go to see doctor carriers, they not just give you a medical prescriptions, they also will give you application prescriptions. They will tell you, go back home, deploy this technology, use these devices, do a monitoring. You can manage for some simple cases. Yeah. Here probably show you, you go back based on the symptoms you are going to monitor, and then you find the IoT devices, services, you deploy your environment. And then you carry out, you collect the data, analyze the data, and then based on the health and care services, and also based on your own situation. Yeah, that is the user modeling and profile, so that the services can be provided to you based on your particular situations. Yeah. So this is how we envision technology can be integrated in a real-world scenario. Not only you talk about to carers, doctors, but in this whole process, your family members, your relatives, even yourself will be kept informed. So that is what we envision, future integrated healthcare ecosystem. But what are the requirements, the key component and functions? So that is something we has been thinking and working on that. So the first element is the IoT modeling, discovery, and services. We will not expect doctors, clinicians, they know IoT knowledge. They know which sensors, devices they will use. And it's also not manageable to handle the IoT manually in industrial scale. So we have to develop some mechanism to formally model, describe, therefore, the sensors devices so that they can be discovered, based on the need. So in this aspect, as you can see, the papers we publish, we have been working, study software defined devices, to represent the IoT in a digital world. Therefore, we use ontologies to describe that so that it can be discovered automatically based on the scenarios. So that's here, the semantic technology is the key. Yeah, so that is, we think it's a key element. Another is about the health and care monitoring infrastructure. If you look at IoT, there are so many devices off the shelf, programmables, in different format. They all use different communication protocols. The data, the signal, they have a different format. And also there are too many application scenarios, self-management, independent living, recreations. So we must develop method and architectures so that we can support, plug, and play in an environment to support that, self-configured, automated. So here you see, so in our research, we develop a service-oriented. Basically, we have a smart environment, smart lab. We develop the underlying infrastructures. So, we can hide the heterogeneity of different devices, protocols, format. They provide unified interfaces. Yeah, so that is the infrastructure. Left-hand side is hardware infrastructure system, and this is how it's used in our studies. Here, just show you our smart lab. You see here various items which are attached with sensors. See this part. Kettles, cups, chairs. That is it. But all these signals will be automatically, no matter what the manufactured from that, the protocols, it will be collected, detected, and the data will be collected and stored to a semantic repository. So when you carry out research in this environment, you do not need to care about the low level. Yeah, you only focus on your application or research issues. Data will seamlessly collected, described in a repository. So that's just to show you that part of work. Another function and key element for that ecosystem is we have to develop scalable data analysis and intelligent processing. There is a wide range of data at multiple levels of abstractions. Yeah. If you think about data nature, there are temporal, spatial, and if you in terms of data type, there's images, text, voice, coming from variables, ambient sensors. There are multi-model sensing, there are multi-source sensing, so wide range data. And for each data, there are different types. You need to go through the different modeling, analysis, and then to the application dependent predictions. So the key is we don't want to reinvent the wheel. Yes, so many. How can we make them customizable, reusable, and reproposable? They can be reused. Here, I think you see here, we are focused on that. In our research, we have developed the semantic analysis. We have applied the deep learning, machine learning, but we all go through, the process from signal to data to information to knowledge. Yeah, but much more work still needs to be done. So how do we, package the transfer learning, for example, federated learning into our utility services so that they can support larger scale applications adopted in the ecosystems. Yeah. Another key element and functions is the user modeling and profile services. Yeah. This is the key to personalized care, precision medicine, and user-central design. There is a holistic personal profile. like in the right-hand bottom figure show. So a user profile not only just about one aspect, a holistic profile will cover physical, social, psychological, emotional, all different aspects. Yeah. Of course, it's a moment. Most research, they just focus on one particular aspect. Normally it's application specific, domain dependent. That is what we did. If you look at this diagram, the right hand top one and the bottom middle one, that is the user profile we developed in our mobile Sage project. The paper should describe that. The challenge is how to generate a complete profile. Yeah, there are many different ways. You can ask the user to do self-reporting. You can observe the behavioral or interactional or some app usage data and perform data mining. Yeah, probably the challenge is how to collect data. That is not just about data; it's about many different aspects. Policies, securities, ethicals issues. So that is the deal. We are working on this in different project or contexts, but just highlight that. Another key element, we have an ecosystem, and we want to deliver something to the user to help them improve conditions or improve quality of life. So that is all done to the decision support. Yeah, but here you can see the health and care application services. They must be adaptable to individual need, but they also has to be done correctly. That means they has to be in line with existing medical care or disease management pathway. I'm not sure whether or not how many of you, talk to doctors. In our, MOSKUS project, we talk to doctors, clinicians. For each medical condition, there always a treatment pathway. There always a care pathway or rehabilitation pathway. Whatever system, digital system you want to provide, they must be in line with this. In this case, formal modeling and the representation of unstructured medical diagnostic expert knowledge heuristics are key. Yeah. So the diagram you see here in the bottom left-hand side is show a generic, the left structure. In the middle is the pathway and how it's downstreaming to lower level in the IT system, and the up level is how it can be practically applied. And the left-hand side is what we did in MOSKUS, arthritis self-management, how we embedded, treatment and care pathway in the decision support system we mentioned in previous slide. But here we say that is indispensable component in the ecosystems. And here, just to give you a very quick simplified open technology platform for such an ecosystem. It covers, front end, IoT physical layer, and then edge and cloud. Yeah. So we'll not drill details based on the time. And here is illustrate in the future how multiple stakeholders from professional staff, from professional carers, how do they interact with patient relative and combining with the healthcare developers and system, IT system developers. Yeah, give rough ideas. This is a vision. There are a number of challenges. If we look at that, that is a depict of the from a commercial perspective. In healthcare no matter is UK NHS or any country's healthcare delivery system, is a complex business chain, yeah, with multiple stakeholders. Each has different views and own industry. And if you look at this diagram, it shows, different stakeholders has different views. The challenge is here, how can we knock down the barriers so different people can talk, understand each other, the concern, the need, they reach a consensus. Only in that case, the solution developed will be acceptable and useful. Yeah. Now, that is from technical challenges. If you look at the ecosystem, and actually, technically, it is boiling down to 3 pillars. Physical world, like IoT devices, and the digital world, data, analytics, algorithm, cloud, and the human world. You are addressing end users, patient. You are dealing with professionals. Everything is changing. Yeah, the challenge is how user behavior and how do they change their behavior, how system behave, how do they adapt to each other, impact each other. And the system, the ecosystem, look at that, is a systems of complex cyber physical systems. How to model the interactions, the system dynamic, how to model the systems behavior. They are all provide huge challenges. Yeah. I will probably very quickly highlight 2 trends. Yeah. The one is user centralized. We already see that, user centralized, we talk about user centralized design. We talk about participatory design. Yeah. And that's what we illustrate here is a typical process, life cycles. How do you develop the user profile? The challenge is moment is this process is static. Yeah, because
can we wrap it up a little bit?
Yeah, it's about just a couple minutes. Yeah. Okay. So that is we need to make it dynamic. Yeah. So it's already not only about the user profile, but also all different aspects. Policy, accessibilities, acceptance. So that is one. So basically, how to embed humans in the design process. Another trend is the disappearance of the boundaries between data and intelligence. So traditionally, you see from data to intelligence, there are 2 separate vertical ways. Yeah, one is data-driven, another traditional knowledge-based system. Both they produce computational intelligence and traditional knowledge-based intelligence. Now, the question is, they are merging. Yeah, they are merging. The key is how do we, excuse me, incorporate human in the loop. Therefore, we achieve hybrid human-machine intelligence. So that's the question is how to embed the cognitive capabilities, how to make the decision explainable, interpretable. Yeah. Therefore, we produce a trusted intelligence system. So this is just a highlight. There are many probably, but this is what we got from our research. So conclusions, very simple. We will say healthcare delivery is changing and shifting, and it's a moment it's a point of the transformation, but the revolution has not come yet. Yeah. And the future healthcare ecosystem is promising. It's a way forward, but its moment is still largely a vision and a work progress, people working on all underpinning fragmented technologies. So future further research on underpinning technology is still needed, but the key is more about multidisciplinary cross-sectors collaboration. all stakeholders has a role to play, and you have to play the role. Yeah, otherwise the solution will not work. Yeah, both challenges and opportunity exist, but it's still a long way to go. Yeah, and you all people working this, we are exciting because there are opportunities, there are challenges. Yeah. So thank you for you listening. Yeah, I will be happy to take questions.
Thank you very much, Luke. I'm conscious about the time because we still have to announce the best paper award for iiWAS, but I know the presentation is recorded, so probably later on the participants can have a look, and then I'm sure, look, if there is any questions, will you be happy to answer questions via email?
Yes, I think I have my information here, and you the slides, you see my papers. If you can drop me anytime, email, or if you have a paper, drop me. Thank you for your listening.
Okay, thank you very much for very interesting presentation, Luke.
Okay, I stop sharing. Thank you, Harry.
So I think now we go to the next sessions, the introduction, the announcement of the best paper awards for iiWAS 2020. And I can please ask my colleague Maria to announce the winner.
Ismail?
Yes, Maria.
Can I get the co-host?
Sorry.
I can share my screen.
Maria, co-host.
Okay, let me share my screen. No, I'm still can't share my screen.
Now you can. Now you can.
Okay, let me try again. All right, okay. All right, everyone. Good evening from Melbourne, Australia. So for this year iiWAS conference, we given two best paper awards. One for the best paper awards, the other one for the student best paper. So this year for the best paper award, we provided to a special team of people that collaboratively work from different country. So good. So the best paper awards this year goes to the paper titled Web Scraping versus Twitter API, a comparison for a credibility analysis. So this paper written from people that work from Peru, France, Venezuela, and Chile. So I think we also need to commend them in terms of the collaborations effort. And this paper shows the good contributions towards the technology for detections of credibility in Twitter. And the paper will be presented tomorrow. So for this paper, you might want to look at tomorrow schedule to see the presentation. So congratulations for Irvin Dongo, Judith Cardinal, Anna Aguilera, Fabio Martinez, Uni Quintero and Sergio Barrios. So that's the best paper for the student. Best paper award. We give that papers to paper title FED-QPL, a language for logical query plans for heterogeneous federation of RDF data sources. So this Sijin Chen is the students and Olaf Hartix is the supervisor. So this work provide a good theoretical work-based work for query logical query plans processing. So they're from Linköping University in Sweden, and their paper will be presented on the third day. So if you can also attend that presentation, you'll be amazed at how good their work is. So that's all for this year Best Paper Award presentations, and thank you to the authors that doing a very excellent job that make the iiWAS conference be successful. Thank you. And I think for the next things that we will have is a break for
10 minutes.
15 minutes now, 10 minutes now. So we'll be back in 10 minutes. We need to get out from this room and then go to the track one of the sessions room, because there will be 3 parallel sessions in the next part of the presentation. Thanks, everyone.